So this is going to be like a kind of developer workshop. So I'm going to go through some coding stuff, and like you're free to follow along if you want. It's probably going to be pretty hard to follow along if you don't have Nargo and Noir installed. So not sure if that's going to work for you, but how do I plug this in?
So once again, let's welcome Kat.
Cool. So I think we got some new people coming in. I'm Kat. I'm a DevRel engineer at Aztec. Aztec is a privacy-first layer 2 on Ethereum. If you haven't heard of us, we allow for private smart contracts and stuff like that. I'm going to be talking about that a bit more in a later workshop that I'm doing, but for today, I just want to talk about writing circuits and specifically writing them in Noir. Noir is our domain-specific ZK language, so it's something that Aztec is developing to make it really, really easy to develop circuits. Before I get started, can I just get a show of hands of people who've actually like written a circuit before in Circum or Noir or Zarkades or anything? Cool. Okay, a lot of this room. Don't know how useful this is going to be for you because this is pretty basic like circuit stuff, but yeah, in today's talk, I'm going to kind of introduce you to Noir, just super basic, writing a few different circuits, very basic stuff. It looks like Rust. It feels kind of like writing Rust, and I'll just talk about the difference between writing functional programming in Rust and writing a circuit in Noir. We're also going to walk through the Alibaba Cave. I'm sure most people in this room have seen that, like kind of an intuition of how zero-knowledge circuits work. But I've got some things that I've added to it to just talk about more of like a snarky Alibaba Cave and non-interactivity and stuff, and how to apply that then to writing Noir circuits and really get an intuition of how ZK circuits work. And yeah, then we're going to apply those things to actually writing circuits in Noir and kind of converting what something might look like in Rust to Noir. So yeah, Noir, we're kind of on the roadmap to 1.0 right now. It's still kind of in beta. But if you're familiar with like Circum, it's kind of similar to that, but a lot easier to use. We're working on making it really fast as well. Noir out of the box uses something called Rettenberg, which is our like proving system. That currently works with Plonk or Turbo Plonk or something. But we're working on it to make it work with Honk as well. So that is Noir. It looks like this. It's just supposed to be easy for anyone to use. This is a program that I will show you in a second, like in VS Code, and we can run it and see what it looks like. But this is literally exactly what it would look like in Rust as well. So what this is doing is it's just defining a main function. You have to define a main function in any sort of Noir circuit that you're writing. It's taking in a private input of X, so just the prover is going to be aware of this, and then a public input of Y. which prover and verifier, and anybody will be aware of what that is. And then it's asserting that they're not equal. And if this all goes through and everything is good, then a proof is generated. So if you're interested in like looking at the code that I'm going to be doing today, you can scan this or just go to this on your laptops. There's 4 circuits in it that we're going to go through. One is just the one that I've showed you, and then there's a couple of others that are just like various things that Noir is capable of, recursion as well, and some other stuff. We've also got some Noir.js in there for playing around. Okay, actually I'm going to show you this. Yeah, this is what we're going to work through. So there's 2 branches. There's main and starter. We're just going to go from starter to main, basically. So I tried to do my own Alibaba cube. I think most of you are going to be aware of this, but for those of you who aren't, this is kind of a proof of like intuition of how ZK works. So you've got Victor here, who's our like verifier, and we've got Peggy, who's our prover, and Peggy is aware of this secret code that opens this gate in here. And so Victor is going to be like, okay, I want to know that you actually know what the secret code of the gate is, but I don't want you to tell me what the gate is. So he's just going to say, hey, come, you're in the cave now, come out through B. And then Peggy's going to do it, and to come out through B, she has to open this gate. And then he's going to be like, okay, you did it. And then this would happen like hundreds of times, and by the end of that, Victor is fairly sure, okay, Peggy probably is aware of what the secret code of the gate is, and I don't need to know what the secret code is. I know that she knows that, so she's proved her knowledge without giving me what that knowledge is. This is, if we go kind of to our Noir and like just have a look at a basic circuit. So I want to zoom in on this. So if you go into that GitHub repo that I showed you and go into just simple, you can see like basically what a setup of a Noir program looks like. So we've got a source file. This has our main circuit in it. And then we have a cargo toml. If you know Rust, this is like cargo toml. It just describes what the project is, and any sort of dependencies that you're going to have will be put in there as well. So in this is the circuit that we showed you. I showed you on the previous slide. Just zoom in more. So it's taking in an X and Y and asserting that they're not equal. So I'm just going to play around with this here, and you can like see how to work with Noir and Margot to prove something really simple. So we can do Nargo check, and what that's going to do is generate the constraint system, and we're going to get a file here called prover toml. So these are just the things that Peggy, the prover, is aware of, and the inputs that are going to go in, including the private input. So if we want this to actually go through as a proof, we've got 1 and we've got 2. 1, like X is 1 and Y is 2, so they're not the same, so that should be asserted. And then we can execute our witness, generate our witness here by doing Margo execute witness. I can type faster than this, but I'm holding a mic. And then when we look in it here, we've got our target thing. This has got our compiled Noir circuit, which you don't really need to care too much about. It's also got our witness file, which looks something like this. It's kind of a mess. You don't need to know what that looks like either. But we can use that witness to then actually generate the proof using our proving backend Berettenberg, which comes out of the box when you install Noir. So we do BB, which stands for Berettenberg, and then we're going to do, written here, prove. We pass in our compiled circuit, which I think is that. And then we're going to pass in our witness as well. And then just wherever we want our proof file to go. So we'll just do target / proof. And then we can see here we have our proof that also looks kind of a bit of a mess. Realistically, this is just like an array of like 114 fields, I think. But this is what it looks like when you do it this way, because it's a G. I don't really know why. It's like a GZ file. Then once we have our prover, we can also verify it. So we can do, we have to generate our verification key, So we'll write our key, bb write verification key. And we pass in the compiled circuit. And the output of where we want that to go as well. And then once we have our verification key, we can actually just verify it. This should just give us nothing if it all works correctly. So we pass in the proof and the verification key. And there's nothing there, which means it was right. But if we make it wrong, then we're going to get an error. And yeah, our verification key is that. So that's kind of just like a really basic Noir program. It's super easy to work with. And you can just use an Argo, which is similar to Cargo in Rust, and use Brandenburg for proving. So now we can do some more fun stuff. So to kind of advance on Alibaba Cave, now with snarks, we don't have that interactivity anymore with Victor constantly asking Peggy, hey, go through this Git, come out this way, and checking and going back and forth. That took a very long time. So we have snarks, which are succinct, non-interactive arguments of knowledge, just to make it a lot faster. And it means that you can't have that interactivity. So kind of thought of this cave and describe it as being sealed. So Victor cannot just keep talking to Peggy and ask what's going on. But in order for that to work, in general, this is not actually super true anymore, but you need a trusted setup. For Aztec, that's what we have. And instead of Victor saying, come out this gate, then the trusted setup is just going to create this randomness of go out the gate B and A. And then Peggy will come out of the gate and open those give the secret key to open the gates, and then take a photo of each of the gates that she comes out of. I'm using the word gate here, and I'm aware that's kind of confusing. And then she puts all of these photos into a proof, gives it to Victor. Victor's like, okay, I have this proof now. I can go check with my shared setup system and get some information from there and put it together. Cool, this is verified. Makes it a lot faster and more succinct than non-interactivity. So this is what it might look like as a diagram. So we've got, this is our trusted setup kind of randomness thing, and Peggy's going in and taking photos of each of the gate, putting them all together and giving them to Victor. And Victor's like, okay, I've got this key and I'll verify it. All right, all good. So kind of want to use that to go back into Noir and do something a little bit more interesting. This looks like a mess. I'm going to get this off the screen. So I have another kind of intermediate circuit here. I've already got the prover and everything set up. But this might be, if you're just familiar with writing Rust, you might be, the intuition would just be oh, I could just pass in some sort of array, and then I can loop through that array, and I can print that array, and that should work. But because it's a sealed cave, you really need to be aware of the size of the circuit before you can execute it. In order to compile it, it needs to have a specific size. It needs to know how many gates and how many constraints are actually involved in it. So you can't just have an arbitrary length of something going in. So if we wanted to make this work, there are multiple ways we can kind of do for loops in Noir, which is a bit more exciting. So I'm going to put this mic down for a sec and actually type. Is there a stand or something? Okay, cool. All right, let's take out this parameter, and we'll go through kind of different for loops that we can do in Noir, and it's fun. So we can do for I, instead of this, we have to specify what the length of a list is, or we can just do something 0 to 5, and this will do 0, 1, 2, 3, 4, 5, and we can print out what I is there. So if we execute that, we should see 0, 1, 2, 3, 4, 5. There's a few other ways you can do it as well. So let's say we do have an array and we're aware of what our size of our array is. So we have these elements, 4, 5, 6, 7, 8, 9. And we can just have the length of that. So for I in 0 to the length of foo, we can do set the element as the the ith element of foo in the array, and then we can print that. See what that looks like. So this should print it in, yeah, it's got hexadecimal, so it's not exactly what it says here, but that's those numbers. And then we can also just do something like for element in foo, print the element. Which should look the same. Yeah. So there's different ways you can do for loops, which I think is really cool. It does just feel like writing functional Rust or something. You just have to be aware that you need to know like the length of the array you're going through. We also do have this idea of breaking and continuing in loops in Noir, but only inside unconstrained functions. So everything that's written in like a regular function in Noir is constrained, as in it's turned into proofs. It's actually proved, it's like constrained. But you can also do things like unconstrained functions. We're going to talk about that a little bit in the next section too. But I think this could be fun to show that you can like make it slightly faster, and you can play with unconstrained functions. So you can do unconstrained function, let's say like break and continue, so we can just see what that looks like. And let's say like for I in 0 to 10, we can like, if I is divisible by 2, so we have the modular thing, by the way, in Noir, which is cool. Then we can just like continue it. Else, if I is 6, then we break. And if we call that from our main function, let's actually print some stuff out so we can see what we're doing here. We'll print I, and then we'll print that we're breaking here. Okay, hopefully this works. Okay, shouldn't have done that. Didn't break. Why did it not break? Okay, this probably has to go first. Okay, not breaks. Yeah, so you can do like breaks and continues and stuff, not with inside constraint functions, but if you're wanting to just have something that feels like a regular program and is still within inside this like sealed kiv, then you can do break and continue inside unconstrained functions. Be aware when you're using these because they are unconstrained, so they're not like super secure. You're not going to want to put everything in here. They're obviously a lot faster and you can do some more stuff with them, but they are not part of the proof. So you can just like put in random inputs in there and then make a proof potentially succeed that shouldn't have succeeded. So let's go our next thing. Some paths take longer, obviously. So a really big part of like what we're trying to do when we're writing circuits is just make them efficient and optimized and the fastest they can possibly be. So like if we go back to our diagram that I made on Canva in like 10 minutes, we have like A, there's only one gate in A and there's 2 in B. So Peggy's going to want to pick the gate that goes fastest and be able to do some things that are faster than that. So we want to write our circuits that use as fewer gates as possible and have as little constraints as we can. So go back to our Noir. We have an optimized thing that we can play with as well. So we've got a function here that gets a square root of a number, uses a pretty typical algorithm to do that by just constantly like dividing it and trying to find a number, and then gives you what that number is. This takes This is very difficult to do in ZK because it just is so time consuming and very expensive. So we can actually see how many ACIR opcodes this is. If we go, am I on the right thing? Yeah. We can do Nargo info. And we can see these opcodes. So whenever you compile something with Noir, it like compiles down into what we call ACIR, which is abstract circuit intermediate representation. And this is what makes it backend agnostic. So you can use like Gros 16 or Halo 2 or whatever you want with, you can write like a backend that works with ICIR with Noir if you don't want to use Brettenberg for whatever reason. So you can see the opcodes here. Generally, you want this number to be smaller, but some opcodes are just more expensive than other ones, so it's not particularly exactly what you want to get down. It will depend on the proving system that you're using. But you can compile it using Brettenberg, which we're going to do in a second, and then you can see how many gates it has, like if you want to use the Brettenberg backend or whatever one you want to use. So let's do that. So now we've got it here, and we can see how many gates it is by doing BB gates. This is going to check the gate counts in Brettenberg and pass in our JSON. And we can see the circuit size is over 3,000. Not too bad, but I think we can get that down. So if we do what we did kind of earlier and use unconstrained functions here, we can actually do it in a way that still is accurate, but we can play with unconstrained functions. And this is kind of a fun part of using unconstrained stuff, is that you don't have to constrain everything, but you can still prove that something is true from an unconstrained function. So we can just make an unconstrained function that's like square root. Unconstrained function. And we can take in the same things here and return the same thing. And we can literally do like all of that in an unconstrained function. And then in our main function that's actually going to be constrained and generating the proofs, we can call this square root function, and then we can square the numbers. And if they return if they're an accurate, like return something true, then we can just assert that that was real, and we should be able to get a smaller circuit because we're not doing all this math inside a constrained function, but we're still getting a accurate asserted response. So now we can execute that. Our prover's got 9, which is like a square, so that's a square root of 3. So we can just, what is this? Yeah, it returns 3, so it returns the square root of it, which is cool. And then we can do the gate count again. I'm just going to recompile it and check the gate counts and just make sure that it's gone down. Yeah, our circuit size is slightly smaller. So I think it was like 3,070 before. Now it's 2,768, and we have way fewer opcodes as well. I think it was like 200. Yeah, 288, and now we have 7. So yeah, you can kind of be like fun with it.
Can we ask questions now?
Yeah.
So, I'm wondering what are the types here. So is this square variable type U32 by default, and is this multiplication of U32 according to it?
We have like multiple different U integers that you can use. So this is like an unsigned integer of 32 bits. There's also, I think we have 64. I just use 32 as like an example that you can use.
Yeah, so the specific question is if this constraint is in the field or in user table.
What do you mean constraint in the field?
So if this multiplication is checked in the underlying field of the system, or
Yes. Yeah, exactly.
because then it will not work, right? I mean, even if the square doesn't exist. Yeah, so in the field, you can take square root of 3 or 5 or whatever. So you will find a witness even if there is no square root. Yeah, maybe you can take it offline because these are like some very, very details of how this is implemented.
Yeah, so if we like change, I don't think this will pass if we change the prover to be like 20 or something, because it shouldn't.
It will not pass because you will be the
Yeah.
witness, but maybe I can find a witness. Depending on how this is implemented, right?
I mean, if the inputs are constrained to 32 bits, then the most you
Yeah,
can
yeah, yeah. So
get
that's the
is
question.
the
That's the
result of the
question.
multiplication 64, and
Yeah, yeah,
inside
yeah.
is probably larger.
Yeah,
The question is if the square root is enforced to be a UN32
Yeah.
or it's not enforced to be a UN32. That's the main question.
But was the type explicit there?
Yeah, it was. I think this is just an abstraction though.
Yeah.
I don't think this is
Question
constrained to be
when
U32.
you do let square equals, does it enforce square to be a UN32 or does it not enforce anything like that?
I don't think it does, but I will need to check.
We have a types defined types.
Yeah.
Scale to the unconstrained function, so yeah,
Right, so I guess the question is that if we have an unconstrained function and with a certain output type, does it enforce that output type on the square?
I don't think so, but I'm not actually totally sure how this is working.
Unconstrained will only be used in proof generation, right?
Yeah.
Yeah. Yeah, I think we can take it offline. It's interesting, but let's not.
Cool. Yeah. Let's talk about it. Cool. Yeah, that's the optimized thing. And then wanted to talk a little bit about like oracles and stuff. So if you're playing with data from the outside world, you obviously can't just like trust that data is going to be true. So you can do these things, ZK oracles, and playing around with those a little bit. And then they can have like verifiers and stuff for their own verifier if they want. Final thing I want to talk about, I think I'm running out of time, caves within caves. So this is a really cool thing Noir can do. It's really powerful. It's recursive proofs. This is kind of what Noir is built for. It's what Berettenberg is really built for and what it's supposed to be really good at. Where you can verify a proof inside another proof and then just continue doing that kind of process. So that's generally how ZK rollups will work, is that you verify the execution of something within another thing and you just keep rolling that up so that you only have to verify once at the end. And when you do that verification at the end, that verifies all the proofs in one verification. So it just makes things a lot faster. You can do that. This is a mess, but you know what it's like. It's like a cave. We kind of call them inner proofs, and then you have this final proof at the very outside of the cave. And then whenever you're doing these other proofs, you're not actually verifying within that proof, but you're like generating the proof verification that will then make it a lot faster to verify at the very end. So I don't have too much time, but I do want to show you a little bit of how that looks in Wire. So we have two circuits here. We have a main, which just looks like what we're used to. In order to make it recursive, we do have to tell the backend, like, hey, can you generate this proof artifacts in a way that can actually be recursive? So you just need to give it a flag. Yeah. I'm just trying to. not going to fight with Git right now, but yeah, you just define it as recursive like that, and then that's going to make our function recursive. And then if we go into our other circuit, this is the one that's actually recursive, so it's going to be taking in the verification key and the proof that was generated from this other circuit on the public inputs. And then, hold on, let me just do something. Ooh. Okay, this is what it looks like, so I don't have to type it out all the time. But yeah, we're just calling verify proof from the standard library, and we're passing in the verification key, the proof, the public inputs, and the hash that we've generated from the verification key with Peterson. So then that's going to verify a proof, and then you can do something else in here. So I kind of want to talk a little bit about just like things you can do with recursion. Don't think I've got too much time. But like, say you're playing a game and you want to just have your play at the game, you want to like prove that that is an accurate play, then you pass that over to your friend, and then your friend can prove that they have an accurate play and give it back to you, and you can verify their proof and keep it going, and then you just publish that final proof like on chain, and someone could verify that the entire game was accurate and good. So yeah, that's the end of the presentation. I hope you learned something about Noir and how powerful it is. Thanks.
Thank you. Right. So thank you, Kat. I believe we have space for one question, I think, if anybody. All right.
Couldn't unconstrained loops or arbitrary jumps within a Noir program be implemented as recursive proofs internally, but to the user it would look like arbitrary jumps, or at least loops? We could do that using another recursive proof being generated, and then the Noir language itself could build kind of a binary tree, for example, to prove it very quickly and in parallel. And so we could simultaneously prove all the execution of a loop of with an arbitrary number of iterations.
Wait, what's the question? Can you?
Could it be possible, or is there any problem with implementing that?
With what? So trying to verify a function within an unconstrained function?
We're trying to execute loops with an unknown number of iterations.
Okay.
And this could be just a wrapped way of we wouldn't know that we're recursively using proofs as a user.
Yeah.
But yeah, this could be done.
I think, my intuition is saying that would be possible, definitely. Cool.
Right. So once again, thanks, Kat. Give her a warm round of applause. And right now, next up is a lunch break. So let's meet in an hour and a half.